we will be looking at the count of an event in a given period of time, and what we will find is that under certain assumptions the count follows a Poisson distribution. To get started, let's define X to be the count of an event in a given period of time, let's say from 0 to small t, or from cap t to cap t plus small t. Now, in our discussion, we will simply stick to the interval from 0 to t, but the discussion equally applies to the interval from cap t to cap t plus small t. So once again, cap x is the number of occurrences of an event in a given period of time, and the period is from 0 to t. Let's let r be the rate of x per unit time, or the mean of x per unit time. In other words, on average, the count of the event is r per unit time. So if the unit of time is hours, then on average we expect to see r occurrences of the event per hour. Now, for x to have Poisson distribution, there are three assumptions that are required. So let me describe the assumptions now. Assumption number one is that the probability of getting exactly one occurrence in a given interval of length h is equal to r times h plus little o of h. Now, for now, let me say that little o of h is a negligible amount. So if I ignore little o of h on the right hand side, then what number one is saying is that the probability of obtaining exactly one occurrence in a given interval of length h is proportional to the length h, and the constant of proportionality is r, the rate of x. Okay, now what is little o of h? Well, little o of h represents a function of h. So little o of h represents a function of h such that the limit of the ratio f of h over h is 0 as h goes to 0. So for example, f of h could be h squared. Well, then if I look at the limit as h goes to 0 of h squared divided by h, we get the limit as h goes to 0 of h, which is 0. So h squared, so h squared is little o of h. So in other words, if you think about this limit here, what it says is that when h is close to 0, the function f of h is substantially smaller than h. Okay, so the little o of h is basically a quantity that is a negligible amount. Alright, assumption number two. The assumption number two is the probability of obtaining two or more occurrences in an interval of length h is little o of h. In other words, what we are saying is that the probability of getting 2 or more occurrences in an interval of length h is negligible. That is, it is rare that 2 or more occurrences will it is rare that 2 or more events will occur in an interval of length h when h is small. So when h is small, it is rare that 2 or more it is rare to have 2 or more occurrences in the interval of length h. Assumption number 3, in order to describe it, I have to introduce some notations, so bear with me. Let n be a positive integer. Let I1, I2, in be any set of n non-overlapping intervals of time. Let J1, J2, Jn be any integers, non-negative integers. Let E1, so let E1 be the event that E1 be the event that we have exactly J1 occurrences over the interval I1. E2 is the event that we have exactly J2 occurrences over the interval I2, and so on. And we have so on En. En is the event of getting exactly Jn occurrences over the interval In. Okay. Then assumption number 3 is that the events E1, E2, En are independent. In other words, what assumption number 3 is saying is that whatever happens in one interval has no effect on what may occur in other non-overlapping intervals. That is this. So whatever happens in one interval has no effect on what may occur in other non-overlapping intervals. Okay, so at this point you probably should pause and look at the assumptions again and again. Make sure you understand the assumptions. I am also going to pause for a second and start. Alright, so fix the interval of time from 0 to t. X be the number of occurrences in the interval from 0 to t. What we want to show is that the PMF of x, the probability that x is k, is e to the negative lambda times lambda to the k over k factorial over where lambda is r times the length of the interval t. So the first thing that I'm going to do is look at the interval from 0 to t, and I'm going to divide the interval into n subintervals of the same length. So each subinterval has length t divided by n. So the partition points of the subinterval, the partition points of the interval would be then 0, t over n, 2 times t over n, I minus 1 times t over n, I times t over n, n minus 1 times t over n, and the last one is t, which is n times t over n. So we divided the interval from 0 to t into n subintervals having the same length t over n. The interval from 0 to t over n, that's the first subinterval. Then I have the second subinterval, this is the ith subinterval, and the last one from here to here, that's the nth subinterval. Now what we need to do is we need to take a closer look at the interval, the event x equals to k. So let's take a closer look at that event, because we want to find the probability of that event. So consider the event x equals to k. Now I am going to divide this event into two exhaustive events. So let's divide this event into two exhaustive events in the following way. So what x equals to k means that there are k occurrences of the event or the phenomenon over the interval from 0 to t. So on this interval from 0 to t, there are k occurrences. Well, since there are k occurrences, there are two possibilities. One is that there are k subintervals containing exactly one occurrence each, or there is at least one subinterval containing two or more occurrences. So let me write that down. So there are two, if there are k occurrences over the interval from 0 to t, then there are two possibilities. So let me denote by A one of the possibilities. So A is the event that A is the event that there are k subintervals containing exactly one occurrence and the other n minus k subintervals will contain zero occurrence, and the other n minus k sub intervals contain no occurrences. Okay, and the other possibility, if there are k occurrences, the other possibility is that there might be a subinterval containing two or more. So let B be the event that at least B be the event that that there are k occurrences and at least one sub interval at least one sub interval contains two or more occurrences. Okay, so these two events are exhaustive events. That is, the event that x is k can be divided into these two exhaustive events a and b. In other words, the event that x is k is the union of a and b, and this is a disjoint union, obviously. Okay, so what we need to do now is find the probability of a and b, because if we can find the probability of a and b, we can then find the probability that x is k. Okay, so let's look at the probability of the event b. Clearly, the probability of the event b is less than the probability that at least one of the subintervals contains two or more occurrences which is the same as the probability that either the first subinterval contains two or more, or the second subinterval contains two or more, or dot dot dot, or I want to put the commas right here, or the nth subinterval contains two or more. Okay, so then notice that it means the probability of the union I going from 1 to n, the ith sub interval contains two or more. Now this is less than or equal to the sum I going from 1 to n of the probability of the event that the ith sub interval contains 2 or more. Well, what does our assumption number 2 say about that probability? Well, assumption number 2 says that the probability of getting 2 or more occurrences in an interval of length h is little o of h. Alright, so using that, look at the ith subinterval. The probability of getting 2 or more occurrences in the ith subinterval, which has length t over n, is little o of t over n. So assumption number 2, the ith subinterval has length t divided by n. So the assumption number 2, so equal to, so this is by assumption number 2. What we could say that this is the summation I going from 1 up to n, and that probability is little o of the length of the ith subinterval t over n. Now each summand is little o of t over n, and there are n summands, so then we could say this is equal to n times little o of t over n. Okay. Now I am going to rewrite this as n, I'm going to rewrite this as t times n divided by, so I'm rewriting n as t times n over t. So notice that t cancels out and we still have n, times little o of t divided by n. So once again we rewrote n as t times n over t. This will be equal to, I'm going to keep t, and n over t, I'm going to put it below little o of t over n. So if I want to put n over t below little o of t over n, I have to write t over n. Make sure you understand that algebra. So okay, let me explain that algebra. It's like saying if I have 2/3 times, let's say 5, and what I'm writing is, I'm writing it as 5 divided by 3/2. Okay. Alright, so now I have little o of t over n divided by t over n. Now remember the definition of little o of something. So remember that little o of h represents a function such that if you divide that function by h, it goes to 0 as h goes to 0, right? So then what we see is that is the following: as n goes to infinity, then t over n goes to 0, and so the little o of t over n over t over n converges to 0. Right? That's by definition of little o definition, right? Little o of t over n represents a function of t over n such that if you divide it by t over n, it goes to 0 if t over n goes to 0. So then I can say this is equal to t times 0, which is 0, and again this is as n goes to infinity. So this happens as we take the limit as n goes to infinity. So what we have found is that the probability of B goes to 0 as n goes to infinity. So remember, n is what? N is the number of subintervals of the interval from 0 to t. So if we divide the interval from 0 to t into more and more subintervals, then we can make the probability of B to go to 0. Okay? So let's now find the probability of A. So let's find probability of A now. To do that is going to be a little bit of work. First of all, we're going to find the probability that a subinterval contains exactly one occurrence. So what's the probability that a subinterval, that is one of the subintervals, what's the probability that one of the subintervals or a subinterval contains exactly one occurrence? Well, by assumption number 2, so by assumption number 1, this would be equal to, remember the length of the subinterval is t divided by n, and let's look at the assumption number 1. It says the probability of getting exactly one occurrence in an interval of length h is r times h plus little o of h. Now in our case, one of the subintervals has each subinterval has length t over n, so h is t over n. So this would be r times the length t over n plus little o of t over n. Also, the probability that a subinterval contains none of the occurrences or 0 occurrences. Well, what will that be? That's the same as 1 minus the probability that the subinterval contains exactly one occurrence or the subinterval contains 2 or more. Now again, by assumption number 1, assumption number 1 says the probability that the subinterval contains exactly one occurrence is r times the length of the subinterval plus little o of the length of the subinterval. And what's the probability that the subinterval contains 2 or more? Well, by assumption number 2, that's little o of t over n. So we add them. And so what we get is 1 minus r times t over n minus something that is little o of t over n. So if I add little o of t over n plus the little of t over n, if you add two functions that are little o of t over n, you get a function of little o of t over n. Okay, so that's that. Alright, so let's go ahead and look at those two probabilities and make sure you understood those. Now we want to go ahead and look at the probability of A. So remember, probability of A means the probability actually, let me write that before this picture. So let's recall that the probability of A is the same as the probability that k of the subintervals, k of the subintervals contain exactly one occurrence each. And dot dot dot, meaning that the remaining n minus k subintervals contain none. So how do we find that? Well, in order to find this, I have to figure out, first of all, how many ways the event A can happen. In order to figure that out, I'm going to introduce some notation. So in order to find this, what I'm going to do is the following. I'm going to label each subinterval as S or F. So S means that the subinterval contains exactly one occurrence. F means the subinterval contains 0 occurrence. So to find the probability of A, then the first thing I'm going to do is say that, well, we have then n subintervals here. Each one is labeled as S or F. S means the subinterval contains exactly one occurrence, and F means the subinterval contains none. And so the question is, how many ways can we pick k subintervals here? Or, we want exactly k s and n minus k f, right? So how many ways can we label these subintervals so that k of them are s and the remaining are labeled as f? So the question is the following. Well, the answer is, so here's what I want to say. The n choose k is the number of ways we can label the subintervals where k are labeled as s and n minus k remaining ones are labeled as f. Okay, let's call them successes and failures. So how many so we have sort of n possibilities here, and how many ways can we get k successes and f failures, right? So that's n choose k. And now let's pick one specific sequence of k successes and k successes and f failures, right? So in terms of s and f, notice that the probability of s means the probability of getting exactly, probability of s means the probability that the associated subinterval contains exactly one occurrence, and that's the same as this. So this is p of s in terms of my notation, and this thing here is p of f. The probability that a subinterval contains none, that's p of f. So notice that the probability of a then would be n choose k times the probability of s, which happens k times, and the probability of f, which happens n minus k times, which then is equal to n choose k times, remember the probability that an interval contains exactly one is r times t over n plus little o of t over n to the k times 1 minus r times t over n minus 0 times t over n to the n minus k. Now, what happens as n goes to infinity then? Well, it turns out that so remember we took the limit of the binomial distribution to get the Poisson distribution, and we take the limit of this expression in the same way, and we can show that this quantity converges to e to the negative r times t multiplied by rt over k factorial, rt to the k over k factorial as n goes to infinity. So this quantity here, this one has limit e to the negative rt, and we get the limit of the other two factors as rt to the k over k factorial. And I'm not going to show you the details, but you take the limit of that in the same way as you take the limit of the binomial distribution. So then what we have found is that the probability of A approaches e to the negative rt times rt to the k over k factorial as n goes to infinity. So now we could say we remember that we wanted to find the probability that x is k, that is the number of occurrences over the interval from 0 to t, and we said that the event is the same as A union B, which then is the probability of A plus the probability of B. And then what we have found is that this quantity P of A, we know that it converges to e to the negative rt to the k over k factorial, and we know that P of B converges to 0 as n goes to infinity. So the probability that x is k is equal to e to the negative lambda to the k over k factorial, where we are setting lambda to r times t. Okay, so we have seen that the three assumptions lead us to this result that the distribution of x is Poisson with parameter lambda equal to r times t. Okay, so this is a little bit difficult for many of you, but I hope that you can look over it a couple of times and understand how we justified that the count x is Poisson under the three assumptions.